And now I would like to introduce our presenter today, Dr. James Marty. Dr. Marty is a senior scientist at the University of Minnesota Nano Center. We are very excited to have him here with us today. Dr. Marty is renowned in his field of study and is an expert on today's topic. And now I will pass the baton over to Dr. Marty.
Okay, so again, this is a discussion of really what's going on with dynamic light scattering. As from judging from the poll numbers, you're all very familiar with DLS. DLS is found in many laboratories across a wide range of industries, analyzing nanoscale materials ranging from biomaterials like exosomes to pinks, pigments and pigments and inks and so forth. But for many of us, we simply have sat down to work with DLS and really don't always consider what's inside the box. How is it working? Which leads to a discussion of what are its capabilities and limitations, and really how to best interpret DLS results based on these limitations and capabilities. So in this talk, hopefully I'll be able to review DLS fundamentals, non-mathematically for the most part, and examine the different ways that DLS raw signals are processed to yield what we're really interested in, and that is a particle size distribution, and then explore how these different processing schemes affect how to interpret DLS output. When we sit down to analyze a particle sample, of course, we may be interested in a number of different properties. The concentration may be of interest to many different formulations. Particle shape may be of interest for, say, compacting powders in pharmaceutical tableting, for instance. And the particle surface charge, or zeta potential, is always very, very important for dispersion stability. But we are looking mostly now at particle size, and particle size, or sizes, rather, the distribution of sizes, causes a lot of, or is responsible for many of the properties of particle dispersions. So as we consider particles, it'd be nice if our world was dominated by the image on the left, where all the particles were the same size. We could then just specify a number, a particle size. And then if we plotted that distribution, the distribution would look monomodal and narrow, and our troubles would be over. Unfortunately, real world is typically more like the picture on the right, where we have a wide range of particle sizes all mixed together in our sample, and it's our task to determine what is the distribution of sizes in our sample. So one of the easiest way, or the most direct way, is simply to look at particles using either optical microscopy or extending that to the nano region with electron microscopy. This is a direct measurement of particles, and as such, it's quite accurate. You can get images of the particles and translate them into their geometric extent, their diameter. Unfortunately, you get very, very low counting statistics out of this exercise. I don't know if you've ever tried to characterize a sample this way, but you can count for 8 hours, get a few thousand particle data points out of a sample that maybe consists of 10 to the 9th particles. So very low counting statistics and very low confidence that you've got a representative sample. Early on, it became obvious that we need to automate this process in some way. So over the years, a number of different particle size distribution measurement systems have been developed and are implemented in various laboratories. Here I've grouped them into several different groups. The top is single particle analysis using some form of light scattering or electron scattering in the case of electron microscopy. This would include things like optical microscopy. Let's see if I get a pointer here. Optical microscopy, as we've noted, and extending that to automated versions of dynamic imaging and optical particle counters. We can also take a look at groups of particles, and that's what this talk will dedicate itself to generally with DLS. A third method is to take the sample and segregate out the particles into different size classes and then count them after the fact. So a number of methods have been developed for particle sizing, say for larger micron-sized powders. Sieving can be used to separate the sample into different sieves, and then we measure by mass the fraction at each sieve. Centrifugation can be used for dispersions. And for the aerosol particle world, we can separate these things aerodynamically and then count them afterwards. But looking at the single particle counter approach, or the single particle approach used in optical microscopy, one way to automate that is with an optical particle counter. And these are used in a number of industries, in particular clean room certification and also analyzing air quality. The optical particle counter directs particles through a measurement zone where light, it can be monochromatic or white light, is impinging upon the particle. We then collect the scattered light at a detector, and the amount of scattered light is going to be translated into an electrical blip, and that blip will give us a count and a measure of size of the particle. This is a direct light scattering method, and it's reassuring because you're counting one particle at a time and you're resolving individual particles. It has a practical limit, though, of about 200, 230 or so nanometers in size for reasons that we'll get into in a moment, but it is widely used to analyze aerosols with single particle counting. To think about how we can use scattered light to analyze particles, let's consider the interaction of light with matter. When light impinges upon a particle, a number of different phenomena can be identified, such as refraction, absorption, and diffraction. And then these are all used in various ways in particle counting and characterization. But for our purposes, it might be better to think about this scenario where we have light incident on a particle, and we can think of light as a train of fluctuating electric and magnetic fields. As this light wave impinges upon the atoms forming our suspended particle, the electric fields will induce oscillations of the electrons and the atoms in the material. That oscillating dipole will re-radiate electromagnetic radiation, and it will re-radiate it in all directions or sometimes with a specific angular dependence depending on the size of the particle. This intensity is what we're going to measure in light scattering, and it becomes a critical limiting factor in that the light intensity scattered from very small particles, say under 100 nanometers, becomes very difficult to detect because it becomes very, very low level. As an example, consider a couple of particles. One is at 1 micron size. A second particle is 1/100th of that diameter, at 10 nanometers. The relative diameter between the two, that small nanoparticle has maybe 1% of the larger particle's diameter, but represents 1/1,000,000th of the particle volume, of the larger particle volume. And since intensity goes as the square of volume, the scattered intensity from that small nanoparticle will be 12 orders of magnitude smaller than the 1 micron particle, which gives you an idea of the difficulty technically detecting light scattered directly from a single nanoparticle. There's a practical limit below which we just cannot work. So technically, we have to come up with some alternative ways of detecting these really small particles. The aerosol folks have come up with this condensation particle counter. In this case, we have a small nanoparticle. This is typical of a newly nucleated particle in the atmosphere. As this particle is formed, it's made to pass through a region of a saturated vapor. It could be water vapor, could be the vapor from an alcohol or an organic, but this droplet will nucleate, this particle will nucleate the formation of a liquid droplet in the saturation zone, and as it passes through, we now have a droplet that's large enough to be directly counted using an optical particle counter. So this is great. We can count the original nanoparticles one by one. Unfortunately, all of the original size information of that particle is lost. That particle is buried inside this large, relatively larger liquid droplet. And so to get sizing information out of this, we have to do segregation and separation upstream of the saturation for this to work. This has been widely adopted in the aerosol world, but it really is less used in the liquid particle counting world, although there are liquid particle counters that are designed to detect very small trace amounts of contaminants in ultra-pure liquids. In the dispersion world, the more common approach has been to go with ensemble techniques. Ensemble techniques is where we're going to collect the light scattered from a collection of many particles. Now, immediately you may see the difficulty here. If we collected particle scattering, light scattered from many particles, how do we know which particles scattered how much of that light? How do we know what size particles? How do we tease out an actual size distribution from this integrated, mixed up signal? So this ensemble techniques all require some sort of deconvolution algorithm to separate out the effects of different individual sizes particles from the combined signal. And of course, ensemble techniques are represented in the laboratories currently by laser diffraction and dynamic light scattering. I've listed some of the size ranges that are typical for these techniques, but it's worthwhile keeping in mind that the size ranges promised by the vendors are frequently well in excess of what's really practical in the laboratory. Laser diffraction, in my experience, is good down to about 100 nanometers, maybe even a little smaller, but not a great deal depending on the material. And it is up to, depending on your collection optics, up to 2,000 or 3,000 micrometers. Dynamic light scattering, on the other hand, is good down to 2 or 3 nanometers, although some vendors will talk about fractions of nanometer as their lower detection limit. That has not been my experience. We also have an upper limit, practically speaking, of a few microns or so, and we'll see why that is in just a moment. So considering dynamic light scattering's history, if you look in the literature, you see that it's been adapted from techniques that were originally developed to measure molecular species, the molecular weight distribution of dissolved proteins or other types of macromolecules. In laser light scattering, a monochromatic light source, usually now these days laser light, is directed onto an ensemble of particles that are dispersed in a liquid. The particles are typical of those suspended in the liquid in that they are undergoing Brownian motion. They are diffusing. They're diffusing because of the rapid impacts of the molecules of the surrounding liquid phase. And the smaller ones are going to be diffusing more quickly and diffusing farther than the larger ones. This is the core of the dynamic light scattering method, as well as other methods like nanoparticle tracking analysis. Because we need some measurable diffusion distance and Brownian motion velocity, this method is best suited to particles that are below a few microns that have more substantial diffusivity. And I'm sure that you've all seen the ways of, I'm going to turn off my laser pointer here. You've probably seen examples of Brownian motion. This happens to be globules of fat from a whole milk sample suspended in water. And clearly this is the motion that we are going to use for VLS. You may know that this original phenomenon was recorded by a botanist, Robert Brown, who observed pollen doing Brownian motion in a droplet of water. But he assumed that the particles were alive in some way. It fell to Albert Einstein to really complete the picture in determining that Brownian motion is due to the random impacts of the molecules of the continuous phase. In using particle diffusion as a way of determining particle size, we rely upon a couple of relationships that were hammered out quite some time ago. In the mid-1800s, Stokes established that the drag force that a particle experiences as it moves through a fluid, liquid or gas, is proportional to the particle diameter and the fluid viscosity by the Stokes relationship. Einstein completed the picture by establishing a relationship between the particle diffusion coefficient D and the Stokes drag force, giving us the Stokes-Einstein relationship that is, again, dependent on the liquid viscosity, the fluid viscosity here, eta, and the particle diameter, D. So hence, if we can measure and establish the diffusivity of a particle, we can directly relate it to its diameter. As you may know, this is the hydrodynamic diameter. This is the equivalent diameter that a particle would experience as it moves in the same way as you observe here. To effectuate this measurement, the hardware of DLS typically looks something like this. Monochromatic light, again, usually a laser of different wavelengths depending on manufacturer, is focused down onto a small section of a particle suspension sample. Those particles will scatter light in many different directions. A portion of that scattered light is collected through collection optics and caused to impinge upon a photodetector, where the photodetector will translate that incoming photon or set of photons to an electrical voltage, which is then recorded. The collection angle here can be totally back scattered, it can be forward scattered, it can be 90-degree scattered, or it can be a variable scattering collection angle. It's depending on the implementation of DLS. What we get out of that detector after signal conditioning and filtering out the large DC component is something that may look like this. This is a plot of photodetector output and equivalent to scattered light intensity over a period of time. And as you can see, there's a seemingly random oscillation here really corresponding to that seemingly random walk motion of the particles in the sample. Now, to do dynamic light scattering, we have a jumping off point. We have a fork in the road. There are two fundamental ways of taking this raw data and processing it into something that we're interested in, that is a size distribution. One way would be to examine the overall time variation of that signal. So what we're getting is a signal that's varying in time because the scattered light is varying in intensity. That's due to the scattered light from particles in motion interfering with each other, resulting in a speckle pattern, which is then not constant in time, but changing with a certain time constant. So analyzing and focusing on how that pattern changes with time is the foundation of photon correlation spectroscopy, or PCS. A second approach is to examine the frequency components of that varying signal. As we saw, the lights, or as we'll see, the light scattered from the moving particles is interfering with itself, but it's also Doppler shifting the scattered light to higher and lower frequencies. And since smaller particles are expected to be moving at higher speeds, we would expect them to produce greater frequency Doppler shifts. So since this collected light signal consists of many frequencies, we're going to resolve the frequencies and determine the size of the particles making up that overall signal. This is the frequency analysis or power spectrum method. And it should be stressed that each of these methods can be exploited and have been exploited by dynamic light scattering to obtain particle size distributions, but they are really fundamentally unlike. They're dissimilar. Let's focus first on the details of the PCS approach. If you imagine a sample that's got a couple particles sitting in it, incident light hits these particles or scattered off both of the particles. If the particles happen to scatter light that are in phase, they will constructively interfere at the detector, producing a bright spot, and the detector will turn that into a higher voltage level. If the particles are slightly different in a slightly different position, the scattered light may be completely or slightly out of phase, interfere destructively, and cancel out the light signal. There will be a dark spot at the photodetector, resulting in a low or zero voltage output. You can imagine that interference pattern macroscopically is looking something like this. This is the scattered light from a number of particles that are mutually interfering. In a PCS system, typically we take a look at a small portion of that area, collect the light with optics, impinge upon the photodetector, and get a signal of photodetector voltage, or equivalently light intensity, that's varying in time like this. And the variations are on the order on a time scale of microseconds, or even microseconds. So now our challenge is to take that raw information and get some information about the particles that interfered and produced this signal. The core of doing that in PCS is to form the autocorrelation function. This is a function that considers how fast the scattered intensity is changing by forming a product of the intensity at time t and the intensity at time t plus a small tau here, or delta t, a small increment of time later. By forming the product and integrating over all of the time, all the delta t's, all the taus, we get the autocorrelation function, frequently listed in the literature as G sub 2. If we're going to implement this calculation in digital electronics, we're going to take this continuous integral and turn it into a discrete sum. But the idea is the same. We are calculating, we're multiplying intensity at a certain time, intensity at a time somewhat later. We're getting a value of the correlation between the light scattered at those two different times. The autocorrelation function should decay, and should decay exponentially with time. As particles are changing positions, they no longer have any correlation with their initial position, and so the correlation will decline with time, and that change with time is going to be harnessed to figure out how big the particles are. Typically, you'll encounter not a linear reproduction or a representation of G2, it'll be more logarithmic. So as you go into the literature and look at examples of autocorrelation functions, or if you look at some manufacturer's software will give you the autocorrelation function of your PCS machine, it'll look something like that. So the intensity correlation should decay exponentially, and it should drop more quickly for smaller, more faster moving particles. If we have a sample that consists of one size particle, then it's fairly straightforward to use that correlation decay to calculate how large the particle is, or how large all the particles are, rather. And we can distinguish between particles or samples of small particles or samples of large particles by the rate of decay of the autocorrelation coefficient. Now, this, unfortunately, is not the case that we have a completely single-sized particle, but it's the starting point for using autocorrelation to examine a real sample. So if we consider a sample where the particles are mostly monomodal and pretty monodispersed, in other words, they're not too spread out, we can form an approximation of the autocorrelation function as an exponential term with a couple of constants. This is the so-called cumulant expansion, because we're going to take this approximation, rearrange terms, and form the natural logarithm, and expand this expression in a power series in time. As with most series expansions, we're going to count on the fact that time is small, or this variable is small, and so we can disregard the higher order terms. But there is a physical meaning for the coefficients for the linear term and the squared term. The mean, we cast this decay as exponential with a characteristic decay constant of gamma. So we can relate gamma to this first coefficient in the expansion, A1. And since we can relate the decay coefficient with the mean diffusivity, D, we can relate this initial coefficient to mean particle size. This yields what is known as the Z average, or mean particle size in PCS. We can also use this expansion to get an idea of how spread out the size distribution might be. By forming a combination of the first and second coefficients, we form what is known as the Polydispersity Index, or PDI. PDI and Z average are frequently the things that are primarily reported from a PCS size measurement, and they are oftentimes found in the literature as the only numbers that are characterizing a nanoparticle dispersion sample. Now, that works pretty well for samples that are mostly monodispersed or close to it. In the real world, you may, of course, have samples that are composed of a number of different sized particles. And in that sample, or if we measure the decay constant, we'll find that each particle size has a characteristic decay constant. What we measure is the combination of these different particular exponential decays. It's worth noting that the sum of exponentials is not an exponential. And so this overall integrated signal cannot be modeled strictly with just an exponential decay. The method of cumulants is going to break down. And if you need any proof of that, here is a printout of one of the tools in my laboratory. This is a sample that was clearly not monodispersed, and it did not have a narrow size distribution or narrow PDI. So the software is throwing up this warning. The sample is too polydispersed for cumulant analysis. Suggests we rely on other types of analysis. In this case, it's called a distribution analysis. What this means, though, is that for polydispersed samples, or samples that are somewhat widely spread, we have to go to a different method. And in PCS, this typically takes the form of assuming a type of functional form. Could be log normal distribution, or if we know that there are two different particle sizes present, we can adopt a bimodal model. But these are models that are resident in the PCS software, which we can then use to try to fit the observed autocorrelation decay with some that we know about, particle sizes that we know about. The most common way of doing this is a class of methods called non-negative least squares fitting methods. And there's a number of very sophisticated fitting processes that have been developed over the years and are found in most commercial software for PCS devices. So in this method, it goes something like this. We are going to have a set of particle sizes, and we know their corresponding decay rates that they should exhibit. We'll then select some sort of distribution form in rough sense. Could it be Gaussian, or could it be bimodal, it could be log normal. Our process is to then, with a linear fitting process, we're going to obtain the weightings for each particle decay constant such that the aggregate will match our observed autocorrelation decay. The outcome then is a logarithmically scaled histogram of particle sizes, and this is what comes up when the measurement is done on your screen. The problem with all of this, the difficulty, is that this is a difficult, ill-posed problem, and many solutions can be found that may satisfy the mathematical expression that we are trying to work with and match. So to some extent, the solution will depend on the form that you went into this assuming. If you assumed it was bimodal, the outcome will attempt to fit the data to a bimodal distribution. Now, PCS software, as I mentioned, has a lot of very sophisticated forms of these fitting routines, and so it now gives the user options of how to vary certain parameters to better fit the original measured autocorrelation function. That should be done with caution, however. This is an example from a recent paper that took gold nanoparticles and measured them with atomic force microscopy after being deposited on film, and that was treated as the ground truth particle size distribution. The authors then measured the same dispersion with a PCS system using non-negative least squares, and then varied the parameters and found that the dotted line, which is the AFM measured size distribution, could only be matched by rather severely torquing on the parameters that were changeable in the algorithm. So the bottom line is that your first answer from a non-negative least squares may require some additional information to try to adjust it to the actual circumstances, the actual condition of your sample. So in summary, photon correlation spectroscopy depends on the light scattered by moving particles interfering at the detector, creating a speckle pattern or a pattern of varying intensity that changes in time. The changes in this light intensity are quantified using the autocorrelation function, and the decay of that function is described as either an exponential or a set of exponentials for well-behaved, fairly monodispersed samples. For multimodal, multi-peaked, or polydispersed samples, the correlation function then must be fitted using the models that you can choose, and perhaps you have some information that brings you to choose a more appropriate model over another model. The default outputs are the z-average size and the polydispersity index of the distribution. Turning now to frequency analysis. In this case, we're not looking at, we're still looking at intensity. We're still using a detector. We're still using monochromatic light impinging upon our sample. In the sample, you can imagine particles are moving in all directions at once over a range of speeds. Particles that are moving directly away from the detector will scatter light that is redshifted or lower frequency back to the detector. Those that are moving towards the detector will scatter blue shifted or higher frequency scattered light. The detector will collect this and will collect it again as an intensity. It's going to take those incoming frequencies and turn them into a voltage. In this case, though, these random particle motions will produce a distribution of optical frequency shifts. And so if we plot the intensities of these shifts against frequency, omega in this case, we'll get what is known as a power spectrum. And the power spectrum is the starting point for frequency analysis. It should be noted that the power spectrum and the intensity of the autocorrelation function are related. If we consider the way that the signal is varying in time, as PCS does, and do a Fourier transform with this data, that is to say, calculate the frequency components that are inherent in this oscillation and plot those frequencies as a function plot the amplitudes of those frequency changes on a plot and get a power spectrum, we'll get the power spectrum starting point. So the two methods are related in that regard. For frequency analysis, though, we can calculate the expected frequency shift of particles based on their size, as well as several other factors in the experiment, such as the collection angle, temperature, and liquid viscosity. We can expect then smaller particles to create higher expected central frequency shifts. Larger particles will create a smaller frequency shift. And here's a representation maybe of some definite defined particle sizes plotted with their frequency shift in a logarithmic frequency channel form. So in a frequency analysis approach, we are going to start with this varying intensity signal, resolve the frequency components that are found in this signal, and then plot the frequency shifts on a logarithmic scale of frequency shift. In this case, this example, we know that we've got some larger particles, 140 nanometers, and with some smaller particles at 10 nanometers, which are producing a frequency shift higher in frequency. And again, like any real system, it's all overlaid on top of each other. Our job now is to determine what particle sizes make up this set of frequency shifts. For this, we're going to use an iterative inversion process, similar to what is used in laser diffraction. So we are going to start with an estimated size distribution, an initial guess, which can be a pretty informed guess depending on the initial shape of this power spectrum. We're then going to calculate a synthetic power spectrum based on that estimated size distribution. Compare that to the actual power spectrum measured and calculate the error, the discrepancy between the two. Based on the discrepancy, we can correct our initial guess and create a new synthetic power distribution or power spectrum, can make the comparison again and iterate this process until the error drops below a certain acceptable level. The outcome then is the size distribution that is plotted at the end of the process on your screen. There is some technical difficulties that we need to overcome, though, if we're going to do frequency analysis. And that is these frequency shifts by the part of the light scattered by particles are quite small, maybe up to a few thousand hertz. And that's occurring against a backdrop of very high frequency light optical frequencies, which are 10 to the 14th hertz or so. It's really difficult to pick out that variation directly against an incident light frequency that's so high. But fortunately, the phenomenon of beat frequency comes to our rescue. You may have seen this demonstrated with audio frequencies, where two frequencies that are slightly displaced in frequency, two signals, will mix, and what will occur is a beating frequency, which represents the difference between the two interfering frequencies. So by allowing the scattered light to interfere with the incident light, we can create a beat frequency that slowly oscillates slowly enough to be easily detected by conventional electronics. There's a couple of different ways of arranging this interference process. One would be to let the particles interfere with themselves. This is in fact how PCS is working. The particles in a sample are scattering light. The adjacent particles are interfering. The light scattered by adjacent particles are interfering, and that interference is detected as light or bright spots on the detector. If we instead, however, we take the light scattered from a sample and allow it to interfere not with its neighbors necessarily, but with the incident light, we get a much different method of forming the interference. We get that beat frequency improvement for one thing, but we also get a much higher intensity signal. And for mathematical justification, you can consider that the power spectrum for a self-interfering or self-beating system has a strength that's proportional to the product of that, or the scattered intensity, average scattered intensity squared. Since this value of intensity is typically quite low, this is a very small prefactor for this number, and so our power spectrum is going to be of a relatively low magnitude. If, on the other hand, we interfere the scattered light of the particles with the incident light, then the prefactor is the product of the scattered light intensity and the incident light intensity, which is orders of magnitude higher than that scattered light. As a result, if you do the interference this way, you get a power spectrum raw signal that's hundreds or millions of times that which with the self-interfering method. So the signal to noise ratio is substantially higher when used in this fashion with frequency analysis. And this is maybe one of the greatest advantages of this method. Practically, to realize this in a practical lab tool, the laser is oftentimes emitted and passed down an optical fiber pass through a probe which is immersed in the sample. Particles out here are going to be impinged upon by that laser light. Will scatter laser light in all directions, including back through the probe window, where it then travels along the same optical fiber, or at least for part of the way, and then goes up to the detector. But we are, since we have the incident light present here, we can form an interference signal at the beginning here, and have this heterodyne interference setup happening at the detector with this arrangement. So in summary, frequency analysis depends on the notion that moving particles scattering light back to the detector are going to Doppler shift that scatter light. The shifted frequencies are going to mix with, and in heterodyne arrangements, are going to be interfering with the incident light. That creates a beat frequencies, which makes up the intensity signal. We can take the intensity signal and deconvolve or resolve the frequencies in it, and then relate the frequency shifts to particles of known size. Now, note that this approach does not explicitly need to assume a form of the distribution going in, but it does require an inversion process. It's still an indirect measurement of particle size, in that you have to use iterative inversion, to determine the concentrations of each size particle that produced our raw signal. Comparing these two methods, one is inclined to take a look at historically. When the early literature arrived on DLS, frequency analysis was frequently being used, and it was initially explored, but I think it dropped out of favor because at the time, researchers were using spectrometers, which are analog instruments prone to noise. It couldn't really be implemented on a digital system. And so that's the reason why photon correlation spectroscopy was really the first to market, and has in the years since gained a wide market share. PCS was easier to implement on digital electronics, digital comparators, counters, multi-channel analyzers, pulse height analyzers, and so forth. And so as a result, it really forms the majority of commercial DLS instruments in the present use, at least in my experience. It's so widespread that oftentimes authors and reviewers assume that DLS is synonymous with photon correlation spectroscopy. Frequency analysis arrived later and really had to wait upon the development of some new technology. It has been implemented by several manufacturers over the years. Presently, to my knowledge, it's only implemented by Microtract MRB, but it should be noted that both techniques are spelled out and accepted by the International Standards Organization. The ISO standard 22412 spells out how to perform nanoparticle size analysis with dynamic light scattering, and it explicitly mentions both PCS and frequency analysis, or power spectrum analysis, in the standard. So the question is either technique better? To define better, we have to say, well, which technique is likely to give us a more accurate final size distribution over a wider range of sample types? And for that, we have to consider, well, what distribution are you really talking about? It should be noted that the raw DLS output is what's known as an intensity-weighted distribution. Typically, we are interested in knowing where the particle volume or mass resides in our sample. That's a volume distribution, or how many particles reside in each given size range or size channel, a number distribution. So just a review on size distributions. As I've mentioned, number distributions are plotting the number of particles in a given size, particle size channel. And that's oftentimes useful for things like nucleation studies or learning, finding out individual discrete particle populations. The volume distribution is plotting the amount of total particulate volume in each given size range. This might be more important for you if your product is a particle and you want to know where the product is ending up, like in, say, pigment manufacturing or pharmaceutical drug manufacturing. Any of these distributions can be plotted not as terms of true numbers, but in a percentage of the total particle number or volume present. And this is typically how we encounter it in DLS, because we don't get absolute concentration numbers out of DLS, at least not directly. So these two distributions of the same particle sample will look very different, as you have probably encountered if you've ever switched back and forth between number and volume distributions. Here's a case of 250 1-micron particles and 5,000 100 nanometer particles. By a number distribution, the impression is that this sample mostly contains nanoparticles. And numerically, you're right, the population of small one dominates. But in terms of particle volume, these small ones contribute very little. The volume distribution reveals that most of the particulate volume resides here, up at 1 micron. And so this is a very common exercise in particle science. Which distribution should I present? Volume or number? This is complicated by the fact that DLS's raw signal is in the intensity of scattered light, and this is deconvolved initially to an intensity distribution, a distribution of particle size based on how intensely it scatters. Well, since we've already seen that scattering intensity is a strong function of volume, it's going to be dominated by larger particles in the sample. And again, the intensity distribution is sometimes useful if you have no further information about your suspended particles. If you do not know what they are, you don't know what the refractive index might be, then the intensity distribution will give you metrics like the z-average size and the polydispersity index. And for some samples, especially there's those that are highly polydispersed, that might be the best you can hope for. Unfortunately, it's not what you may really want for your analysis system. So to convert intensity distributions to more useful forms, we're going to make use of a couple of scattering theories. That one formulated by Lord Rayleigh, which covers light scattering from particles that are much, much smaller than the wavelength of incident light. Rayleigh scattering is the theory that explains why the sky is blue, for example. In 1908, Gustav Mie was able to apply Maxwell's theories of electromagnetism in a rigorous fashion to light scattering by particles, and came up with a theory that describes light scattering in more general cases, particle sizes that are at or above or close to or below the size of the wavelength of light, particles of arbitrary shape. And in particular, Mie spelled out the angular dependence of light scattering that comes about with particles that are at or close to the wavelength of incident light. And it turns out that converting the raw intensity distribution and using these theories requires knowledge of your system, in particular, the refractive index of the suspended particle, the refractive index of the surrounding bulk phase, and the liquid viscosity. So since we need to define refractive index of the particle in particular, this is only applicable to a uniform particle composition sample. We cannot really accurately use these theories for mixed heterogeneous samples. Going from intensity to volume to number is a function that can be done with the click of a button on most commercial DLS systems. And you'll notice if you have a nice monodisperse sample, here's the PSL calibration sizing standard, we would expect that to be very narrow and well-defined. There really isn't much difference in the particle mode and mean given by each of these representations. For a polydispersed sample, this is a sample from my lab where we were synthesizing inorganic nanocrystals. In a synthesis reaction, you're going to usually get a wide spread of particle sizes, and indeed we do. The intensity distribution looks like this. The volume distribution still has some larger particles out here, but shifts this mode somewhat smaller, and a number distribution really is dominated by the much more numerous small particles, which do not contribute much in volume. So they don't show any. There's very few large particles shown here, and the summary of that is like so. Your measures of your mean particle size will, that is to say, mean or mode or standard deviation will differ greatly. So when you are quoting or describing your particle size distribution with one number, say mean, it's very important to specify what representation you're referring to. So to do some conversions from the intensity distribution, there are many caveats. To really reliably do that transformation, we really rely on an accurate starting point. That is to say, an intensity distribution that has the highest accuracy and the lowest errors. Polydispersed samples are inherently more difficult to convert between the different representations, simply because the uncertainty is somewhat larger in polydispersed samples. In the process of doing the conversion, though, I have to give the advantage to frequency analysis, at least those that incorporate a heterodyne interference system, for the reason that the signal to noise ratio of the raw signal is vastly higher than what you get with PCS. Because you have a more higher signal to noise ratio, you have a much more robust and probably more accurate intensity distribution to start with, especially for the very small particles under 200 nanometers that scatter so very little. I think it's telling that in the training materials that manufacturers of PCS-based instruments give you, they will explicitly caution you not to convert the initial intensity distribution to volume or number with their tools. It says nothing to stop you from doing that, but they caution you that it's not a good idea. So converting to volume distribution, in my experience, my frequency analysis-based system that I have in my lab, I found it quite reliable. PCS, going by manufacturers' recommendations, they say really do it for high quality intensity data where you've got strong signal, and the more monodisperse, the better. Now, should you convert to number distribution? I would caution users not to do this. I caution my students not to do this. Because for either PCS or frequency analysis, this is yet another greater extrapolation from the primary data. You're stepping farther and farther away from the data that you have. Any noises or inaccuracies in the intensity distribution will be magnified in this transition, thereby giving less reliability to a number distribution. My suggestion would be, if you really need to do this, restrict your conversions to samples that are highly monodisperse, or consider other techniques that do number distributions more directly. For instance, nanoparticle tracking analysis is a native way of counting individual particles and forming a number distribution. The flip side is that you're counting many, many fewer particles, and so your counting statistics are not as attractive as with DLS. All right, so that's the first part of the talk, which I talk mostly about DLS. I want to leave some time for questions, so I'm going to go through these next slides fairly quickly, but I want to encourage all users that you need to be skeptical of your output. Any analytical technique requires your knowledge, your interpretation to be a valuable measurement. So let's consider some of the ways that things can go wrong. If your particle size range is outside that of DLS systems, it's not going to be a good measurement. If you expect a greater particle size range up above maybe a few microns, consider other methods like laser diffraction or optical particle sizing, or even electrozone sensing. If you have high or low concentrations in your sample, you can see effects on your derived particle size. High concentration can cause intermolecular forces like van der Waals attractive forces to cause single particles to act in a correlated way and sort of act like they are one particle. The extreme case of this is where close range forces will agglomerate the particles, and now all of a sudden you don't have your fundamental particle size anymore, you're measuring the agglomerates. High concentration could also decrease your derived particle size distribution because of multiple light scattering. As light enters a crowded particle system, it may be scattered, and some of it may be scattered out to the detector, but the portion of it will be further scattered, and then ultimately multiple scattered out to the detector. This muddies the picture, and the net effect in most cases is that it decreases particle size. Low particle concentration, of course, has its own problem, and that is you just don't have much of a signal. Low signal to noise ratio is the bane of many dilute samples. In some cases, you simply have to find a way to concentrate this sample to make a DLS measurement on it. Large particles are, again, the bane of our existence sometimes. A few stray contaminant particles are large enough to dominate your intensity-based measurement, and they will oftentimes come through any conversion and dominate your derived size distributions as well. Those particles large enough to settle or float, if they're lighter than water, less dense than water, will create spurious motion signals, and motion, of course, is the basis of our measurements, so we have to scrupulously avoid large particles with sample treatment via settling or filtration, or other methods. Use other methods that have a wider size range. Noise is something that sometimes you have control over, sometimes not. Noise in the form of fluctuating temperatures is something you have control over. Fluctuating temps will change the viscosity, and hence the calculation will not be as accurate. If your system does not already have a thermostatic stabilizer, a thermostatic bath, then that's something that you probably want to try, or at the very least, make sure your sample is well equilibrated to room temperature so that you haven't just taken out of the fridge, it's changing temperature and the viscosity is changing as you go. Stray vibration is a problem in any method that's going to depend on measuring particle motion. And you need to ask yourself sometimes, is my sample in a steady state condition? Is it undergoing agglomeration or is it stabilized? Even reactions sometimes have occurred when, say, adjusting pH. Dirty cuvettes or windows are things that produce light scatter, bright signal that interferes with the raw collected signal. These are things that oftentimes your system can warn you about a noise issue. Electronic noise is usually constant and usually can be compensated within the within the software simply by a 0 or a background setting. So to conclude, I'd like to just leave you with the notion that yes, DLS is still the single best method to analyze a large range of types of nanoparticles over a fairly wide size range. However, to obtain good results, the practitioners of DLS really should have an understanding of how the raw signal is collected, how it's processed into a final size distribution that you then collect, and how that process may affect measurement reliability for a range of different types of samples and sample sizes. Using your skills, you're the judge of the veracity of DLS systems, and you're the ones are able to make the judgment of how well the measurement is matching reality. And my argument is understanding how it works, how things under the hood affect how it works, can improve that judgment of your measurement accuracy. Got some references and further reading, which are downloadable in the download packet. Vast literature on dynamic light scattering and its development. I encourage you to delve into it. And so I'd like now to turn it over to Terry to help with some questions and discussion.
Okay, thanks, Jim, and let me thank you for an outstanding presentation. We do have a number of questions here. First of all, I'll answer the one that gets asked the most. Will the presentation be available? It will be available. It will be sent to you as a recording in the package that you will get in an email in a few days, maybe up to a week. And with that, I'll get to the first question here, and it's a question that a lot of us asked when we first got into using DLS, and of course it involves getting to the volume distribution. The question is there any way to measure particle size distribution for particle mixtures of different refractive indices using dynamic light scattering?
To my knowledge, you're restricted to the intensity distribution, which if you can prepare your sample so that large particles are not there, then perhaps that would work well. We could also fall back on the separation notion. Perhaps you could collect different particle size cuts from your sample, such that each cut is going to cover a relatively narrow spread, and then use the intensity distribution, which does not require knowledge of refractive index, directly on that. The fallback position would be if your particles are under 1 micron, use something like nanoparticle tracking analysis, which doesn't care about refractive index.
Okay, thanks, Jim. We get down here, we have some questions on viscosity. Since viscosity is important in the calculation, how do you deal with non-Newtonian continuous phase?
Very good question. I've encountered some papers that explore this, and I really can't say that I would be an expert on this. I know that some practitioners have, for certain types of samples, simply taken the overall viscosity of the dispersion as opposed to the viscosity of the background continuous phase. I don't know the range of applicability of that approach, and if that would help with non-Newtonian fluids. That's a fascinating area, and I think it's something that I need to learn more about.
Okay. We have another one here. What makes a solvent acceptable for DLS? Is there any reason a relatively viscous by optically transparent material like an epoxy resin would be unsuitable?
Well, viscosity, of course, is as it goes up, you're going to see lower diffusivity. So since that's the signal you're measuring, it may be more difficult. Your signal will drop. It may require longer periods of time for measurement. Honestly, the upper limit of viscosity is for DLS would be hard to fathom. I think we would have to undergo some measurements to determine how viscous the medium really could be before it's simply not giving you a signal. For autocorrelation, we have to have variation, or we assume variation over a set period of time, microseconds for the individual variations, and then making maybe an individual measurement that's on the order of milliseconds to seconds. I don't know frankly, what would happen if we tried our system on a very viscous system that would require tens of seconds or minutes of analysis of collecting the autocorrelation function. That is that'd be a good exercise to push your machine to see how long it would go. Maybe you would have to modify some aspect of the software to allow that long-term measurement. But in theory, as long as we could get a set of variations to construct an autocorrelation function over a relevant time frame to the point where the scattered intensity correlation goes to baseline, you should be able to collect that information in a very viscous system.
Okay, thanks, Jim. We have one here that is asking which nanoscale objects, especially metals, are unique. And I think I would interpret that as meaning, are there different types of samples that perform differently in DLS?
In terms of metals, there's nothing intrinsic about a metal. I think what is more important is particle shape. The types of suspended materials that are not perfect spheres, but are rather elongated needle-shaped devices, or platy materials like clays, those are going to diffuse somewhat differently. And I believe there's a literature that addresses how to adjust for non-ideal spheres. But really, what we're measuring ultimately is the equivalent hydrodynamic diameter. We're measuring the way something is diffusing through a continuous medium as if a particle of that diameter would. So if the material being measured is not spherical, if it has high aspect ratio, or if it's a flat platy type thing, you're going to get an answer. I'd have to delve a little bit more into the literature to determine how that's related to the answer. The answer you get, how that's related to the true properties of your sample, if it's extremely non-spherical, for instance.
Okay. Next question here. Are there any instances where homodyne method might miss something that heterodyne might catch? And I think I know the answer to this, but I'll give it to you.
Well, actually, Tara, I think that you should probably answer that, because you've worked with both systems from the engineer's point of view.
Well,
I mean, in essence, I think the big drawing card of heterodyne interference is the much larger signal-to-noise ratio. You simply get a clearer signal of that diffusion behavior, by not just a little bit clearer, but orders of magnitude clearer. So I think that's the primary difference. Sorry, Terry, I didn't mean to step on you.
No, it's no problem. Okay, next one is any limitations with organic solvents, for example, hydrophobic particles?
In my experience, it doesn't really matter too much as long as your system can stand it. If you're using cuvettes, make sure they're not going to dissolve in your organic solvent. If you're using a probe type system, you will need to make sure that probe window is not going to be degraded by the solvent. So for most organic solvents, I think it's full speed ahead. I wouldn't put it in, say, fuming sulfuric acid. For that very little material will stand up to that. But I think that's a practical apparatus question. The theory and the operation of dynamic light scattering shouldn't be affected by choice of organic solvent.
Right. Okay, here's one. How about particles which are agglomerates or aggregates? Would they be disrupted in the process?
DLS is a very non-intrusive method. It's not going to do much to your particles besides simply collect light scattering off of them. If particles are agglomerating, you're going to measure the agglomerates as well as those unagglomerated fundamental size particles. Laser diffraction systems frequently, and other types of circulating particle sizers, oftentimes incorporate some onboard ultrasonics, which can apply some ultrasonic energy and break up at least soft agglomerates. Dynamic light scattering will not do that. It's very gentle and will simply measure what you give it.
Okay. Here's a question. What fluids besides DI water are typically used?
I think users in the field probably have encountered all manner of particle dispersions in organic solvents, like in the pigments and inks industry, or electrolytes, buffers, like are used in the biological field. Practically any optically clear material with well-characterized refractive index and viscosity can be used to suspend your particles. Now, there are better choices than others. You want something that has a refractive index that's stable over the temperature range that you may be working in. You want to make sure that it's transparent to your laser wavelength. But really, the fluids that you can measure suspended particles in are vast, and really it's your choice. That's not the case with, say, measuring zeta potential, where the electrolyte present may affect your measurement of zeta potential. But for size, using dynamic light scattering, I'm not aware of any restrictions on your suspending liquid.
Right, right. Next question is, will colored dissolved materials interfere with particle size measurements?
Colored dissolve, so if like we're measuring, say, biological particles in a growth medium that's like red or something like that, I imagine it would.
I think that's what she means.
Yeah, there's definitely going to be some absorption depending on the laser light wavelength and the absorption properties of the liquid. So this is a case where if you can get by with dilution, with serial dilution, and try to clarify that suspending continuous phase, I would try it. I would at best, you're going to get an attenuation of the laser, the incident light strength, and thereby your scattered light will also be attenuated. If you're dealing with very low scattered light signals already, you can't really live with too much attenuation through that colored medium. It's going to set up a problem. Specifically, what the limit cutoff would be, that's something you would have to establish with your particular materials. But clearer is definitely going to be better.
Right. Well, that does it for questions, except that there were a number of comments saying thank you very much for a great presentation. So applause. And with that, I'll turn it back over to Aaron.